Alright, we're going to look at a problem that is a very simple optimization problem. This is not a spatial optimization problem. It's just made out of two variables, and we're going to try to solve it visually using a graph. Okay, so I'm going to write down the problem formulation. We have here a maximization problem. The reason why I put it to the top right is that I'm going to use the left space to draw the graph. Maximize 2x1 plus x2, okay, subject to, and here are the different constraints. The first one is minus x1, okay, plus 2x2 okay, should be less or equal than 10. Okay, the second one is x1 should be less or equal to 6. You have x1 plus x2 should be less or equal to 14. Okay, and the last one is x1 minus x2 should be less or equal to 6. Right, and also x1 and x2 should be positive, so greater or equal to 0. So now how are we going to visualize this and try to solve it? So I'm going to draw a quick graph and take over in a couple of minutes. Alright, I just drew a graph, x1 here along the x-axis, x2 along the y-axis. And I'm going to basically try to find what we call the feasible region. So first thing we want to do is to map these different constraints or inequalities rather. x1, x2 greater than 0, so x1 x2 greater than 0, that would be this direction. X1 greater than 0 would be this direction. So this one is pretty straightforward and will be mapped. Okay, another one easy to map is x1 less or equal than 6. So how to go about this? So I will basically count here 6 units. So 1, 2, 3, 4, 5, 6, approximately. Okay, it's not perfect, perfect here, but it's quite all right. Right, and I say anything in that direction. Right. So now what we know is that this here is going to be the feasible, feasible region. Okay. So then we have this constraints here that we want to map. x1 plus x2 is less or equal than 14. So if x1 is equal to 0, then x2 must be equal to 14. If x2 is equal to 0, then x1 must be equal to 14. So what we need to do here is to basically count 14. That's going to be beyond here, of course. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that would be around here. Okay, and the other one here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So let's say around here. Again, like I said, it is not perfect, but good enough. So I can map kind of these two right here, this way sort of, right? And this would be my, this would be that inequality here. Okay, and then we of course want to go this direction. And you can verify this because if you say 0 plus 0, which would be this point here, is less than 14, so that is correct. Okay, we have to map these two here, so I'm going to take a quick break and map x1 minus x2 first, and then this other one right after. Alright, let's go back. I just drew every of these different functions, so I had drawn this one before, I have done this one before. Now I did this one, so minus x1 plus 2x2 is less or equal than 10. So how to do that? So you need to identify some points on the line. So if x1 is 0, then x2 should be equal to 5 in order to equal 10, right? So you have 0, okay, and then this is 5, okay. You can take another example. For instance, if x1 say is maybe 4, okay, so minus 4, so this one must be much higher, and so on and so forth. Okay, so you can play with that. Now, and then the last one is this one, x1 minus x2 less equal than 6. So if this is 0, so if x1 is 0, then x2 must be minus 6. If x2 is 0, then x1 must be equal to 6. So we end up with this is my feasible region. So this is very important, feasible region. This is a term that is quite relevant here. And so then the question is, where is my optimal? And I will show you this right in just a second. Last part, mapping the objective function, 2x1 plus x2. So what we do typically, we make up a right-hand side, so let's say is equal to 10. So then I have to find out what value of x1 would be equal to a certain given number. I'd say 5 here, for instance, then x2 is equal to 0. If I say x1 is equal to 4, then x2 must be equal to 2. And so given those two, if I have these two coordinates, I can map, right? I can map here a line. Okay, that is the line where the objective function is equal to 10. And then I can do the same for 15, right? So 15 would be, of course, parallel. It's a little bit further, right? 15 is here. And then I keep going in the parallel manner, right? And until I reach a maximum where I can't go any further, right? So this will be something like this. I cannot go any further, right? Now, why I cannot go any further? Because this is the last point within the feasible region. If I keep going, I'm outside. Okay. Remember, the feasible region is here, and so this here would be where that optimal is located. Okay. So this is one way to solve the problem visually with a graph. Okay. And remember, it's basically I have this almost like a line, and I'm pushing. So remember here, this is my feasible region. I know the solution is somewhere there. Okay. Now, just think about this for 1 second. What if we had a minimization problem? So the same a minimization. So it would also go this way. Okay. But it would stop right here. And then the solution would have been 0, 0, which makes a lot of sense because if we want to minimize, then we put everything equal to 0. Okay. So this is one way. Now, of course, once you start 3 variables, 4 variables, this is impossible. But this is a great way to understand the feasible space, the different constraints, and then how we can maximize and push towards one of the solutions. There are issues where, as you will see later on, sometimes the objective function runs parallel, right? So then you don't have one solution, you may have an infinite number of solutions, things that we will talk about next week.